Hello my friends and welcome to the final part of this course, part 10 on model selection and boosting. So in this part we're going to see three important things, the final tools that I would like you to have in your toolkit. And these are first the k-fold cross-validation technique, which will allow you to measure in the most relevant way the performance of each of your future machine learning models. Then I will teach you grid search, which is a technique that allows you to find the best version of a model by finding the optimal parameters leading to the best score of performance. So if you're doing regression, well, you will find the optimal hyperparameters to find the best R-squared. And if you're doing classification, you will find the best hyperparameters for the highest accuracy. And then that's the final bonus section of this course, let's say. I will teach you one of the most powerful models in machine learning, which is XGBoost. I really want you to have XGBoost in your toolkit, and then you will just be close to invincible. So let's finish with this. I'm at the same time very excited and a bit moved that, we're approaching the end of the journey, but let's finish on a good note and let's enter part 10, model selection and boosting. But just before, let's make sure that everyone here is on the same page. I gave you the link to this folder right before this tutorial, so make sure to connect to it. And now there we go. Let's enter part 10, model selection and boosting. All right, and so as we said, well, we have two sections, model selection, where I will teach you k-fold cross-validation and grid search, and then the final section, XGBoost. So let's start with model selection, and let's start with Python as usual. And in this folder, you will find two implementations this time, one for k-fold cross-validation, where we will implement this k-fold cross-validation technique to find the best accuracy, because we will implement this for a classification problem, actually the same one as in the classification part, so that we can stay familiar with the dataset and focus on the technique itself. And then in the next tutorial, I will teach you grid search, which we will apply on, the kernel SVM model, which we implemented in part 3 with the same dataset. And for this model, we will find the best hyperparameters, the best kernel, the best parameter C, and maybe other hyperparameters. We'll see. So let me just quickly remind what this dataset is about very quickly. So remember, this is a dataset of a car company which has just released a brand new luxury SUV, and it is trying to understand through this dataset, well, which customers buy SUVs, so that we can then train a machine learning model, a classification model, to learn the correlations between these two features, age and estimated salary, and the dependent variable purchased. All right, so each row of this data set corresponds to different customers, and for each of them we have the age, the estimated salary, and whether or not they purchased a SUV in the past couple of years. Okay, so that was a quick reminder, and now let's focus on our first technique, the k-fold cross-validation, and therefore let's open this implementation on either Google Collaboratory or Jupyter Notebook. Feel free to choose your favorite. I'm opening it with Google Collaboratory as usual. And now the notebook is loading. It is laying it out. And there we go. Welcome to the k-fold cross-validation implementation. All right, so as usual, this file is in read-only mode. So we're going to create right away a copy by clicking File here and then Save a Copy in Drive. This will create a copy, and inside which we will be able to re-implement not the whole implementation, because you're going to see that all the cells of this implementation are the same as in the kernel SVM implementation we made in part 3, except one cell, which is the cell, of course, where we implement this k-fold cross-validation technique. So I'm going to show you all these cells here are, for the data preprocessing phase, to which we added that feature scaling tool. Then we train indeed the kernel SVM model on the training set. So just as in our previous kernel SVM implementation, then we make the confusion matrix to do, a first evaluation of the model with the accuracy on the test set only. And here, there we go. That's where we apply k-fold cross-validation. And this cell, which I'm going to remove right away, is the only difference with our previous implementation of the kernel SVM model we implemented in part 3. Because the last two cells here are the same. We visualize here the training set results on this 2D plot, and same for below. We visualize the test set results on the same 2D plot. Okay, so we're just going to re-implement k-fold cross-validation here. so that we can add in our mini toolkit an extra tool to measure the performance of any classification model. All right, are you ready? Let's do this. So let's create a new code cell here. And first, remember that in order to get the Google Colab Assistant, well, we need to run the notebook. And to do this, well, we can either run the first cell or upload the dataset. So let's just do it right now. So I just clicked on this little folder here to access the files of our machine. And right now the notebook is connecting to a runtime to enable file browsing, which we should be able to do in a second. We should be able to see the upload button. There we go. So let's click upload. Then please find on your machine, this machine learning A to Z codes and datasets folder, wherever you put it on your machine. I put it on my desktop. And then let's go inside. Let's enter part 10 model selection boosting, and then section 48 model selection, Python, and that social network ads.csv dataset. Click open, then click OK. Now we have the dataset into our notebook, and therefore we'll be able to get the assistance of Google Colab when applying k-fold cross-validation. Are you ready? Now, once again, you have two options. You can try to do it yourself first by checking out, of course, the Scikit-learn API, the documentation, or, we can just do it together. Anyway, we're on to the finish line here. I'm already super proud of all the work you've provided within this course. This is a huge course. So if you want, let's just finish this together on the best note. All right, let's do this. So, as you understood, we're going to start from Scikit-learn because indeed we're going to grab a tool from the Scikit-learn library to implement this k-fold cross-validation technique. So Scikit-learn, from which we're going to get access to, that model selection module, which is also the name of our section here. Model selection module, because this is the module that contains, of course, the cross-val score function, not a class this time, but just a function, which will perform the k-fold cross-validation on our training set. Not the data set, we have to apply it on the training set because we always want to have this separate test set to test the deployment of our model on brand new observations on which the model wasn't trained. So this k-fold cross-validation technique is supposed to be called on the training set. So let's do this. Let's import that cross-val. There we go. I was waiting for Colab to help me. Cross-val score function to implement the k-fold cross-validation technique. All right, so as you understood, k-fold cross-validation consists of creating a certain number of train test folds. We're going to say 10 train test folds because 10 is the commonly chosen value. So it consists of creating 10 train test folds on which you're going to train your machine learning model on each of the train folds and at the same time test it separately on the test fold. And therefore, since you have 10 train test folds, you will end up with 10 different accuracies on different test sets, like 10 different test sets. And therefore, this is a much relevant way to measure the performance of your model because, this makes sure that we don't get lucky on one test set. When measuring the performance of the model right here on this test set when making the confusion matrix, we get here 93%, but we could have randomly chosen a test set on which the model got lucky when making its predictions. It's totally possible. So here we are creating 10 different test sets, but the correct term is test folds, so as to evaluate the model on different test sets and therefore reducing any risk of getting lucky on a separate test set. Right? And of course, the final accuracy we'll get will be the average of the 10 accuracies obtained with the 10 test folds. All right, so this is exactly what this is about. And therefore, now what we're about to do is create a new variable which we're going to call accuracies, and which will simply be the list of the different accuracies we get by testing the model on the 10 test folds, and in which, of course, each accuracy is the accuracy obtained on each of the 10 test folds. So we're going to get first this list, and then we'll compute the mean of all the accuracies in that list. All right, and how can we get that list? Well, of course, we're going to get it thanks to this cross-val score function. So let's call this function right away, cross-val score. Thank you, Google Colab. And inside which we're going to enter 4 essential parameters, which are first the estimator, which is your classifier, the same one we created in that cell, that classifier here. Then we'll have to input the features of the training set, right, which is xtrain, then the dependent variable of the training set, ytrain, and finally the fourth and last essential argument, which is of course the number of folds we want to have when performing k-fold cross-validation. So I told you 10 as an example, but it is also the most common value, and that's the value we'll choose. All right, so let's input these parameters. As we said, the first one is estimator, and that is of course our classifier, which is our kernel SVM model. Then the next one is the features of the training set. Therefore, we have to enter here xtrain, and the name of the parameter is x. Okay, then same for the dependent variable values of the training set. And for this, the name of the parameter is y, and this is equal, of course, to ytrain, right? The ground truth of the training set, basically. And finally, the number of trained test folds we want to have, which is given by the parameter's name CV, and that we choose to be 10. All right, and that's it. This will not only perform the k-fold cross-validation technique, but at the same time return these 10 accuracies resulting from deploying our model on the 10 test folds. Okay, and now we're going to end this with two beautiful prints, right? This time I'm going to make a much more beautiful print than this one, which just prints the accuracy in this format. But check this out, we're going to make a much more beautiful one by using the format function in Python 3. This is also something I would like you to get and that I would like you to know how to implement. So let's do this here. We're going to start directly with the print, right? Print. Then we're going to enter in quotes, well, first accuracy this way to, clearly specify that we're printing the accuracy. So that's just a string. And then inside a pair of square brackets, just like that, we will enter inside the format of the accuracy. And I would actually like to print this with 2 decimals after the comma and as a float, of course. And the way to do this with this format technique in Python is to specify here colon point to f, meaning exactly that it's going to be a float with 2 decimals after the comma. Okay? And then, since we're not going to display it as the form of here, for example, 0.93 but 93%, well, I'm going to add a space here and then percent. Okay? So that's what you have to enter within the double quote. But then, outside of the double quotes, you need to add a dot here and then this format function in which you're going to input exactly the variable that corresponds to this value here with this specific format. And therefore, what you have to enter here is exactly the mean of the accuracies in that list. And the trick to do this efficiently, to compute this efficiently, is to get that variable, that list of accuracies, and then we're going to use a pre-built method of a Python list, which is very simply the mean function. And to use this, you can just add here a dot just after your list, and then mean with some parentheses. And that's it. This will compute the mean of the 10 accuracies within that list. And of course, since we want to have it in the percent format, here we need to add times 100, right? In order to transform this from 0.93 to 93%. Okay, good. So this line of code prints the accuracy. We could stop here, but it would actually be very interesting to also print the standard deviation. Because since we're getting 10 different accuracies, well, it would be very interesting to see what variance we had among these accuracies. For example, let's say that the mean of the accuracies in that list is 93%. Well, we would have 2 very different situations if on the one hand we have some accuracies close to 98% and others close to, let's say, 84, 85%, but all of them averaging at 93%. That's the first situation, and that situation would be very different than having some accuracies very close to 93%, like 92, 93, 94, 92 again, 94 again, etc. Close to the average. And that's something we can get with the standard deviation, and that's exactly what I will add here as a final line of code inside this k-fold cross-validation cell. So I'm actually going to copy that line of code, and then just below, I'm going to do another print, which is the print of this time the standard deviation, which will be exactly, the root of the variance of these accuracies. And same, I'm going to choose to have a float with 2 decimals after the comma. And here, well, to compute the standard deviation of the accuracies within that list, well, we need to replace that mean function by std. The std function, which computes exactly the standard deviation of values within a list, within this accuracies list. And all good. Now we're ready for the final run. I'm just going to run everything again to see what will be this most relevant measure of the accuracy and at the same time the standard deviation of the accuracies within the test folds. All right, are you ready? Let's do this. Let's click runtime here and then we can just do a restart and run all. Here, if you're sure you're ready, let's click yes and let's do this. Now all the cells will be running as we can see, and first we're going to get again the 93%, but here let's see what we get. Well, of course, we get a different accuracy than the one we get here. And that's because I told you, we can be a bit lucky when evaluating the accuracy of our classification model on this specific test set. This is a single test set on which the accuracy can totally be indeed a bit higher than the average accuracy over 10 different test sets. And this is exactly the case here, because when we get 10 different test sets, well, we get that the average accuracy of the 10 accuracies resulting from these test folds is indeed 90.33%. And that makes much more sense, and this is actually the real or most relevant value of the accuracy for this specific model, the kernel SVM, on this specific dataset. And let's see what the standard deviation is. So it is 6.57%, and that means only one thing. That means that more or less, well, the 10 accuracies resulting from our test folds fall more or less between 90.33 minus 6.57 and 90.33 plus 6.57. In other words, they fall around between 83.5% and 96.5%. And so we have actually a pretty high standard deviation, and that's good to know because, that's a very different situation than if we had, accuracies falling between 89 and 91, for example. That would be a low standard deviation. All right, good. So now you have this K-fold cross-validation technique in your toolkit. So you're now packed with the best and most relevant way to measure the accuracy of your classification model. And now we're going to move on to the next section, because now that you have this most performant measure, well, I would like you to also have the technique that can find the optimal values of your hyperparameters in your model. These parameters that are not trained. And I will teach you how to find the best values. So as soon as you're ready for this next section, well, join me. Let's do this together. And until then, enjoy machine learning.